for his talk in this additional lecture series. I now request Professor Aptame Pal to chair this session.
Okay, yeah. So it's a great thing to have Rahul from Johns Hopkins. So yeah, as we can already see, he will talk about statistics of automorphic representations and advanced trace formulas. Yeah. Over to you, Rahul. Yeah, please proceed.
Okay. Yeah, so thank you for the introduction. And again, thank you so much for the chance to be able to speak in the seminar, even to take up 2 whole hours here. Right, so yeah, so this is sort of the second part of a two-part talk. In the last talk, I discussed maybe how you can use trace formulas, sort of versions of the Arthur-Selberg trace formula, to answer maybe statistical questions about automorphic representations. And we specifically discussed Arthur's invariant trace formula and how it might simplify in some special cases, and how that would help you answer particular questions about particular kinds of automorphic representations. So in this talk, we'll talk about how we can use maybe some more modern developments and stable trace formulas and like maybe the endoscopic classification to build on this work and try to understand other more complicated kinds of automorphic representations. So at the very end, I'm going to be discussing some joint work with Mathilde Gerbeli-Gauthier on counting cohomological automorphic representations. So with that quick introduction out of the way, let's begin with the talk. Okay, so I'm just going to mention again that when I give slide talks, I like to sort of color code things in the slides just because there are a lot of details here, and maybe depending on how familiar you are with the material, some things are good to pay attention to, some things aren't. So I'm going to highlight some things in gray. And as before, what the gray means is that unless you're very familiar with the field, you should probably ignore that detail. That's just like a comment for people that have work in this, or just something to make sure that it's not a literal lie on the slide. You can treat it as just like an asterisk. Um, on the other hand, there are going to be things that are in orange, and the things in orange are sort of key concepts that maybe I'll sort of take as kind of background material. So I'm not going to explain them fully, but I'll try to summarize intuitively and precisely how the orange things go. And I think most of the orange things, a lot of them have been mentioned in previous talks. So if you've been following this series, a lot of the orange things can be familiar. Right, so that's the color coding. Okay, so what I'm gonna do for this talk is I'm gonna first like quickly go over a review of what happened in the last talk and sort of fit these problems into the context of everything. And as in the last talk, then I'm gonna talk about some sort of heuristics for thinking about the problem. And finally, at the end of the talk, we're going to go over a particular example of this example of counting cohomological representations. And we'll talk about how the heuristic techniques can actually be like precisely realized in that case. So let's begin with the review of context. Okay, so as I was saying, in the last talk, we discussed how the Arthur-Selberg trace formula is a very good tool for computing counts or statistics of automorphic representations, and it's particularly good when you care about asymptotic counts. Because remember, we discussed that there are multiple terms on the geometric side of the Arthur-Selberg trace formula, and asymptotically, the main terms are kind of the easiest terms. So you can get rid of a lot of complications of the other terms if you just care about asymptotics. So the specific problem that we were trying to solve is what we could do is we could look at all automorphic representations pi on some reductive group. Those automorphic representations, they have local components pi v over places v of whatever number field you're working over. And we would put some abstract condition CV on each place pi on each factor pi v, and we would try to count how many automorphic representations satisfy that condition at every place. So a fruitful strategy that we discussed, and of course it's not the only strategy, but it's a particularly fruitful one, is we can try to look at there's this like sort of spectrum of trace formulas, and towards the bottom of the spectrum, we had a slide there. There are some more abstract trace formulas that maybe in general are difficult to work with and not very explicit. But there's special cases where maybe one of your conditions CV takes some very special form where these abstract trace formulas would simplify very nicely and they become not so bad to work with. So that's the strategy that we discussed. And the example we talked about is there's this particular trace formula of Arthur in an 89 paper for automorphic representations with discrete series ad infinity. And we discussed how this was used in a paper of Shin and Templier in 2016 to give very, very detailed statistics with a lot of nice number theory applications. So in this talk, what we're going to try to do is we're going to try to see how you can use more modern trace formula techniques that have been developed over the last 10 or 20 years to extend this strategy. And instead of just discrete series infinity, we can look at other cases. So that's what we're going to talk about today. Okay, so let's continue. So let's talk about what specific other cases might we look at. So I'm going to explain a kind of framework for thinking about these counting problems. And the key part of this framework is that if we recall from last talk, there's this sort of dictionary between sort of the classical way to think about automorphic forms and the representation theoretic way to think about automorphic representations. And in this dictionary, what kind of happens is that the components of the automorphic representations at the infinite places of your number field. So basically for like automorphic representations corresponding to modular forms, like what the representation at the real place is, that kind of determines what the qualitative type of an automorphic representation is. So remember for GL2, this would sort of tell you whether an automorphic representation was a modular form or a mass form, and maybe what the weight of the modular form is. And this is kind of a good sort of, this is a qualitative distinction, right? So like mass forms behave very differently from modular forms. So we're basically going to classify our questions we're going to sort of emphasize the condition at infinity as a particularly important condition, because that's going to tell us the qualitative type of automorphic representation we're looking at. And that's sort of going to maybe give us a lot of intuition about maybe how complicated the particular counting problem we're looking at is. So this is the framework we're gonna use. So just to remind you guys again, so in this Arthur 89 paper, this particular trace formula for discrete series at infinity, what we had is we had this well, remember the discrete series were classified into these things called L packets, just finite sets parameterized by finite dimensional representations of the group at infinity. And our condition at infinity was going to be that the component at infinity was contained in this particular discrete series L packet. And we were able to choose almost every possible lambda. So what almost every possible meant was that, okay, so lambda is a finite dimensional representation. And basically we needed the condition that the lambda needed to have non-singular highest weight. So remember, there's some kind of like Weyl sector or whatever that classifies the finite dimensional representations, and lambda, the highest weight, can live inside, and it can't live on the boundary. Okay. And basically, on the modular form case, this just means that we're looking at, modular forms of weight greater than 2. Okay, so modular forms of weight greater than 2. Okay, so this is the condition that we had before. Basically, we're looking at the condition that all the infinite component is inside some discrete series L packet. So a new question is maybe what we might want to do is we might want to pick an arbitrary pi naught, and we want to study the condition that the infinite component is exactly equal to that pi naught that we picked. So this is a slightly different condition. It's almost the same because the L packets are kind of small. So for pi naught discrete series, this is basically the same problem as in Arthur 89. There's like an extra step you have to do, but it's been worked out. So yeah, we can look at a single discrete series instead of an L packet. Maybe we can ask for representations in the continuous spectrum, and maybe we can ask for non-tempered representations also. So you can see there's a sort of like, it might get harder or easier depending on what technique you're using and which of these you're trying to do. So this is how we're going to change the question that we're looking at. Okay, so instead of this condition that we had before that was very well dealt with by this Arthur 89 technique, we're going to try to see whether we can extend it to maybe these more complicated questions with more complicated representations at infinity. Okay, so before we go on to talking about how we might do this, or maybe like explicating what more complicated at infinity means in more detail, I need to give a caveat that I'm telling you one particular framework and one particular story, right? So this breaking up the questions by what's going on at infinity, that's just like it's a very convenient way to do it for the particular techniques that I'm using here, where you're trying to simplify abstract trace formulas. If you're using a slightly different framework for the trace formula calculations, there are other ways to think about these counting problems. Um, and depending on the context you're doing and the particular application you have in mind, those might be more natural or this one might be more natural. So I really need to explain maybe one other framework that people think about a lot and that a lot of work has been put into. So this framework is instead of trying to take the invariant trace formula and focus on a case where the invariant trace formula simplifies, you just be very brave and you look at the general invariant trace formula and you just try to say as much as you can about the terms, like no matter how complicated they become. So a lot of authors have used this strategy, like Finnis, Lapid, Matz, Mueller, Kim, Wakatsuki, Yamauchi, and there are many more. Um, and basically, one sort of maybe state-of-the-art thing you can think of that comes out of the strategy is instead of thinking about a condition that you're fixing pi at infinity to be a single representation, what you can do is you can look at pi infinity to be contained in any sort of positive volume or like positive measure subset of the unitary dual. So what's going on here? Well, the representations of the group at infinity, there's a way to organize them into some topological space called the unitary dual. And this space has sort of some discrete points. I mean, it also has a measure in it. So it has some discrete points that have finite measure. Those are kind of the discrete series. And it has this like mass of continuous pieces where like the points have zero measure. But if you kind of take like intervals in this mass of a continuous thing, then you might get things that are positive volume. So you have to do some analytic work. You have to prove some bounds on various intertwining operators that appear in the general trace formula. But if you can pull this off, then you can work with any positive volume subset of this. So just as an example of what positive volume means, in sort of the GL2 case, you should think of this as instead of thinking of a Moss form with sort of a fixed Laplace eigenvalue, you're looking at Moss forms with Laplace eigenvalue in some interval. And this restriction shouldn't be surprising because sort of like all the work of Moss forms on GL2, it's sort of you consider the like from the beginning, from the sort of like original Exelberg trace formula, you have to pick an interval. The thing you can't do is you can't look at non-tempered representations if you need this positive volume restriction. So that's sort of some intuition of what this positive volume thing actually means in practice. And sorry, this is a little bit more technical than I'll go into for most of the talk. Okay, and in addition, for the specific cases of like SP4 if SP2N, people have built up a lot of theory about sequel modular forms. So there's some very strong additional results that you can do in these cases. Um, so I think with these techniques, just because the terms in the trace formula are a lot more complicated, you have to do a lot more work to get any kind of error bounds or precise counts. In some cases, people are able to pull it off, but it ends up being more difficult. And finally, this sort of framework, the work that you do in this framework ends up having like I think it has like a pretty different flavor. Um, sort of when you're using trace formulas, there's like the actual work that you're doing, it's on some spectrum between being like very representation theoretic and like feeling a lot like analytic number theory. And sort of the framework that I'm talking about is like very far over towards like feeling like representation theory when you're actually doing the work and doing the calculations. And this framework ends up pushing you more towards like the analytic number theory side. So like, I mean, you end up bounding intertwining operators and doing like a lot of functional analysis, and maybe you're doing very clever things with L functions, and you're using like approximate functional equations and all kinds of those sorts of things. So, okay, so that's just a caveat. I'm giving one particular framework. There are other things people do. Um, you like no talk is just all of math, right? So, okay. So now that we've gone over the context that this all sits in, let's go into a little bit more detail about heuristics in the particular framework that we're talking about. So again, so remember we're looking at this condition that pi infinity equals some pi naught, right? So we're looking at this particular condition of automorphic representations that are infinite component is fixed to be one particular representation. So when we're looking at this condition, there's an informal ranking of complexity that I like to think about based on the qualitative type of what this pi infinity is. So remember in the previous talk, we mentioned that we first looked at discrete series because discrete series are kind of the easiest kind of representation at infinity. So there's sort of a ranking of more and more complicated representations at infinity that make the counting problems more and more complicated. Okay, so of course, again, at the bottom, the easiest things to deal with are the discrete ad infinity automorphic representations, where pi infinity is actually realized as like pi infinity is a discrete series, and you actually get functions on this L2 space that realize the representation. So the next step above that is, well, we look at representations called cohomological representations. So I think this was mentioned in previous talks when you were when someone was discussing the cohomology of locally symmetric spaces. So these are the representations that appear in the cohomology of locally symmetric spaces. So these are the representations that appear in the cohomology of locally symmetric spaces. And there's a sort of theorem that you can classify them according to a particular invariant of the representation at infinity called its infinitesimal character. So this infinitesimal character is just like maybe if you study the representation theory at infinity, it's maybe sort of the most important invariant that you care about. And you can identify these cohomological representations by what value this infinitesimal character takes. And basically what this means is that is the same as a finite dimensional representation. So, well, okay, so finite dimensionals are not cohomological, but these are the unitary ones with the same, well, if the group isn't compact, but these are the unitary ones with the same infinitesimal character as a finite dimensional representation. So it's basically the infinitesimal character takes on the nicest possible values. So next, you can talk about algebraic automorphic representations. And this is basically you weaken the condition on the infinitesimal character a little bit. So it's still kind of nice, but it's not as nice. And then finally, you can think about general automorphic representations, which are basically all possible components at infinity. So now, of course, well, there are lots of reasons to care about automorphic representations, but one of them is that there are lots of applications to other things in math. And depending on the applications you care about, you have to go a different number of steps up this ladder. So if you care about the cohomology of locally symmetric spaces, then, well, by the name, you only need to worry about the discrete ad infinity and cohomological representations. And certain applications towards analysis and maybe some of the very exciting computer science applications that people have been working out recently also only need these two levels. So if these are the applications you care about, you're pretty happy. You only have to worry, you don't have to worry about things that are too complicated. Well, you don't have to go to the things that are impossibly complicated. Um, if you care about Galois representations and number theory, then you also have to care about the algebraic ones. So you're much less happy in this case if these are the applications that you want. The automorphic problems become a lot harder. And some of the analytic applications, or maybe some of the fancy computer science applications, also need you to go down here. And then, well, general things, they also matter for some applications. So this is basically, it depends on what problem you want to solve. You're happy or you're not happy, depending on how far you have to go. So just to give some concreteness, again, it's just, I hope it's helpful to just go through the dictionary of what this all means on GL2, how this ranking of complexity works in GL2. So again, for GL2 over the rational numbers, automorphic representations on the group G are the same as classical modular and Moss forms, right? Basically, the functions that make up the automorphic representations, they give you classical modular and Moss forms. So discrete at infinity, that means that you're looking at modular forms of weight greater than or equal to 2. So if you remember your theory of modular forms, these are the easiest things to deal with. So the easiest qualitative type, these are the easiest ones to deal with. So cohomological, unfortunately, cohomological is not so much more interesting in the case of GL2. So basically, all you're doing in GL2 is you're adding in the trivial representation when you include cohomological representations. But that's sort of just some accident of GL2 being very small. On other groups, you have sort of strange things like that are kind of in between the case of the trivial representation and the case of the discrete ad infinity. So it's some kind of like interpolation between them. But like when you care about the cohomology of locally symmetric spaces, whatever fits into this interpolation, they come up. So that's sort of how you can think about cohomological things a little bit more precisely, or a little bit more concretely. If you care about algebraic automorphic representations on GL2, basically what you're doing classically is you're also thinking about weight 1 modular and Moss forms. So again, just when you remember your theory of modular forms on GL2, the weight 1 case is much more difficult than the weight 2 or greater case. You have to do special things for the weight 1 case, like doing the Eichler-Shimura on weight 1 is much harder. And then finally, when you look at general, you have to consider all other Moss forms. So as usual, these are kind of the scariest things on GL2 that like conjecturally have crazy transcendental eigenvalues and all kinds of wacky stuff going on. So you can see that sort of how easy it is to deal with on GL2 sort of puts you higher and higher up this ladder. Okay, so that's the GL2 example of how we're classifying our problems. Let's maybe discuss how we can go beyond discrete series now. So remember from that Arthur 89 paper and all the work that Shin and Temple did with it, we have a pretty good theory for working with discrete series at infinity automorphic representations and counting them. So how are we going to get further? So the method here, it's maybe not like completely obvious what you do, but there is a method that you can motivate from ideas around Langland's functoriality. So I think this was discussed in previous talks. So Langland's functoriality. So what it is that sometimes you have abstract like geometric relations between different reductive groups. So some smaller group is related to some bigger group in some way. So like technically what you have some kind of embedding between the L group. So this is something that was mentioned before. You have a map from the L group of H to the L group of G. Then you should conjecturally have some relation between automorphic representations on H and automorphic representations on G. Okay, so how do we formulate this? Well, basically the way we should think about this is that conjecturally, there's a part of the automorphic spectrum of G. So you look at all automorphic representations of G, and there's a part sub H that you should think of as coming from a smaller group H. Okay, So again, this is very vague heuristics, right? Like I'm not saying anything precise here. I'm just saying the way you should think about it, the intuition that you should have to motivate what we're doing. Okay, so what does this word transferred mean? So what transferred means, it means it's formulated in terms of traces and kind of these transfer operators on functions. So basically, what you should think about is that if you take a function on the automorphic spectrum for G, or the automorphic spectrum from G, the part that's coming from H, and we look at the convolution operator, as in the previous talk, and we try to take the trace against that convolution operator on this part coming from H, we should be able to compute it as a trace against something that's literally actually on H. So there should be some way to turn this function f to a function f upper h, and that should kind of be dual to this transfer from the automorphic spectrum of H to the part of the automorphic spectrum of H that comes from G, or the part of the automorphic spectrum of G that comes from H. So that's what this transfer should mean. You should be able to construct these transfers of functions, and this transfer of functions should be kind of dual to how the automorphic spectrum of G has pieces coming from H. So of course, again, this is vague intuition. There are very few known cases where this is actually worked out in any precision. So first of all, if H is something called an endoscopic group, which is just some very restricted version of maps from LH into LG. It's basically where this thing is a centralizer, and there are more conditions than it just being a centralizer. So it's a very restricted kind of embeddings. And there's a little technicality here that you don't literally get the trace on the part of G coming from H, but you get some kind of sign trace. And this technicality, in practice, this is actually good news. It lets you do more things than it would let you do otherwise. So it's actually much nicer that you get that this technicality exists. And I don't have a good intuitive explanation why, but just when you're working out the formulas, it just lets you do more things that you can do this. Okay. And next, if H or G is a classical group, so that's like unitary groups, orthogonal groups, or symplectic groups, then you get some partial info for some extra embeddings from these H's into G's. This is through something called the endoscopic classification. Now, I've always been the terminology here is very confusing. So this first bullet point is endoscopy. The second bullet point is the endoscopic classification. And the endoscopic classification does a little bit extra beyond just pure endoscopy. So when you're reading papers, sometimes it's easy to get mixed up. They say endoscopy and you don't know whether they mean the endoscopic classification or just pure endoscopy. But it helped me a lot once I noticed this distinction and was able to kind of understand which exact thing they were talking about. So the endoscopic classification does a little bit extra. It lets you deal with a few extra cases of H. Although constructing this transfer in the endoscopic classification, maybe that's not actually worked out. So there's some other statements that are slightly more complicated than this like clean transfer statement that you have to use instead and you have to work with. So right, so there are very few known cases. But I mean, we'll try to see what we can do with these known cases. And we have this broad overarching framework in hand. So maybe in the next decades, if people figure out more cases, we can see what we can do with those more cases. Okay, so right. So the key idea that we want to use here is basically what we're going to do is we're going to, instead of trying to count on G, just the representations that we care about, we're going to count those representations plus a bunch of extra noise around those representations. And we're going to try to do that in a clever way that the noise only lives in these pieces that come from smaller groups H that we can deal with. So basically then what we can do is we can take these pieces from the smaller group H and we can subtract those off to kind of cancel out the noise, and we're only left with the part that we care about. So for discrete series at infinity, we didn't get this extra noise, so we didn't have to do the second step. But it turns out that for these more complicated, for these cohomological representations, maybe we'll pick out the cohomological thing we care about, but we'll also pick out a bunch of other things. But we can cancel out those other things by looking at pieces that are coming from other groups. Then there'll be some kind of induction, right? So we understand a group by smaller groups, and eventually that'll bottom out, and we can cancel out all the noise, and we're just left with the parts that we care about. So again, maybe it's not like completely obvious that this is the most reasonable thing to do, but it tends to work. It's what's worked in practice. So this is a strategy that we're going to use. So now, so what's happening is, right, so we have these two cases that we know about. So let's see how far up the ladder those two cases can take us. So what can be done? So of course, as we've said a lot of times before, discrete ad infinity, if you just care about discrete ad infinity, this Arthur 89 paper, it works very well, and that was implemented by Shin and Templier. There's a caveat here that you do need endoscopy to isolate a single discrete series in the L packet. And this whole thing, this is basically what you're doing is you're taking advantage of the sign trace. So because you can take advantage of the sign trace, you can like cancel out the signs between the different sign traces, and you can isolate a single discrete series ad infinity. And this was demonstrated in a paper by Axel Ferrari in 2007, how to actually work out the cancellations and the exact like formalism you use to pick out a single discrete series. So okay, discrete ad infinity, as long as you can do these transfers, we have a pretty good theory, and we can answer questions. So for cohomological, Olivier Taïbi in his 2017 thesis demonstrated that basically using the endoscopic classification is enough. So he had some complicated induction, and we'll try to explain later in this talk how that induction works to explain how to maybe isolate a single cohomological representation at infinity. So beyond, again, in the specific framework that I'm telling you, where you want to isolate a single representation at infinity, there are no known methods for how to do this. So the other framework, what you can do is, of course, you can isolate a positive measure subset of such pi infinity, but you can't isolate a single one. And there's a paper of Finnis, Lapid, and Mueller in 2015 that's maybe a good place to start if you want to learn about this kind of stuff. So beyond, you're sort of in a lot of trouble if you want to understand a single representation at infinity. But if you're okay understanding some kind of open subset of representations that's finite volume, then maybe you can do things. But you're sort of stuck with the very complicated like general invariant trace formula and the very complicated sort of weighted orbital integrals and unipotent terms that kind of come up when you're doing that. Okay. Right. So yeah, so this is why right, it really matters like what application you care about, and you're really like pretty unhappy if you have to go too far up that ladder for applications. So basically there's a sort of like wall between the cohomological and beyond the cohomological, and things behind that wall they're like reasonable problems to try to solve. Things afterwards, you're gonna have to come up with something very clever. And I don't know whether this technique is even the right way to think about it. Like it's just much harder. Okay. So finally, let's talk about when you're using this strategy, what sort of goes very wrong. Because so be like before I said that, yeah, one thing that goes wrong is you only have this these functoriality in like very few specific cases. But even when you're restricted to those specific cases, more things kind of go wrong. And the main thing that goes wrong is basically these transfers F upper H. So when you want to reduce the piece of the automorphic spectrum, just pick out that piece of the automorphic spectrum coming from H. You need to compute this transfer and then work at H. And in practice, computing these transfers is extremely, extremely difficult. And when you try to work out a specific project here, this is going to be the main roadblock, and this is going to be what you spend most of your time trying to compute. So if you care about asymptotics, or if you care about just the main term, of course, what's most important is computing the transfer at central elements. And if you're just looking at the case of pure endoscopy, there's a tool called like the Schleicher germ expansion of orbital integrals. I'm not going to discuss what that is, but it's a pretty good tool, and it tells you that what happens is that it tells you that this transfer depends on the unipotent orbital integrals on the group G. And so you might think that this is great because you can just calculate the values of these transfers by calculating particular orbital integrals on G. But it's a little unfortunate because well, when we had this great Arthur 89 formula, one of the really big upsides of that formula that made it like even better than sort of the heuristic trace formula is that you could avoid these unipotent orbital integrals. And practice, these unipotent orbital integrals tend to be sort of the most complicated ones, and they're quite they're not as easy to deal with. So you're sort of when you need to worry about these unipotent orbital integrals to compute these transfers, you're giving up one of the good advantages of this Arthur 89 result. Um, so it does make your life harder. There is a tool, but it makes your life harder, and you might get stuck in dealing with these unipotent orbital integrals then. For the endoscopic classification and the transfers that come into those, well, the situation is much, 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 much worse. Even existence of these transfers is a wide open problem. So these transfers end up being equivalent to certain kinds of stable transfers that people conjecture in the beyond endoscopy program. And well, you're just kind of stuck if you have to calculate those. You have to do some like very specific ad hoc things for the specific case you're looking at. Um, the resolution in practice most usually is that you restrict your attention to problems where only already known special case or maybe like imprecise bounds on the transfers are needed. So you don't try to like solve the general problem where you have to calculate everything about those transfers like very perfectly and like get these values exact. You worry about special cases where you can calculate those values maybe not exactly, and you can like prove some kind of rough enough bound on the other values that you can actually prove that this is a main term. So this is basically where all the work comes in, like figuring out how to manage these transfers well enough that you can get some kind of meaningful result. Okay, so that sort of finishes the heuristics about how this method works. For the rest of the talk, we're going to get into details about how to implement this method in the specific case of understanding representations with an arbitrary cohomological component at infinity. So I think this might be a good place to stop for questions. We're sort of done with a lot of the intuitive, like sort of fuzzy part, and we're going to get into more technical things now. So does anyone have any questions?
So one maybe silly question, like, so when you are talking about all this kind of endoscopic transfer, so all sorts of theta correspondence and everything you are covering, right? I mean,
Oh, I didn't actually talk about the theta correspondence. So the theta correspondence
okay,
lets you do other kinds of transfers. And
okay.
I haven't learned it well enough to know like how it actually fits into this. I think there's some papers of maybe Marshall and collaborators that have
Yeah,
used like
Simon Marshall. Yeah. Oh,
yeah.
okay. Okay.
That's something, yes. So again, right?
That's
This is something that I have to keep on giving as a caveat. Automorphic
okay.
representation is a very broad field. There are a lot of techniques.
Yeah, yeah,
I'm giving
sure, yeah,
you one narrow perspective, and like there are a
yeah,
billion
yeah.
other
No,
things
no,
you can
that's
do.
fine.
Yeah,
Yeah.
yeah.
Okay.
And yeah, sort of. All of us are sort of in the situation where we want to know as many things as possible because the more you
Mm.
know, the more techniques you have to throw at the
Sure, sure.
um, and basically we just go through life trying to pick up as many as we can.
Yeah, yeah.
Yeah, yeah.
Thanks.
Um, yeah. So yeah, the theta correspondences can help you with constructing a lot of these transfers, and it might be a good way to get a lot of information, and it has been used for like serious results. So yeah. Okay. Any more questions? Okay, so let's move on to our example calculation now, or our example of what we're going to do. So we're going to try to count automorphic representations with an arbitrary cohomological thing at infinity. Okay, so Arthur 89 plus, plus this '07 work of Ferrari. Basically what it did is it did invariant trace formula plus some endoscopy, and it gave you a formula for you pick a test function away from infinity, right? So you pick this test function on a g away from infinity, right? And you want to look at all automorphic representations with the infinite component equaling this particular discrete series that you picked. And you want to look at the trace against the away from infinity component of that automorphic representation. So remember, as an example, you can pick f away from infinity to be the indicator function of some level subgroup. And we talked about before that when you do this, this is basically counting. This is counting the kind of modular forms of that level that live inside automorphic representations with this component pi d at infinity. So this is basically the kind of thing that we sort of previously knew how to do. Okay, so the goal in this section is, well, what we're going to do is we're going to change the blue on top to the blue on the bottom. We're going to take some extra input from the endoscopic classification and try to get a formula for, instead of fixing the infinite component to be a discrete series, we fix the infinite component to be an arbitrary cohomological representation. And well, of course, this is going to be in terms of these conjectural transfers that that sort of are suggested by the endoscopic classification. So we're going to explain how to do this, leaving it in terms of these conjectural transfers. And then we're going to talk about some cases where you can work out enough information of these conjectural transfers to get an actual result. Okay, so that's our goal. So I think maybe, I don't know, this is, I guess, something that's good to remember as you're going through the talk, because I'm going to go I'm going to go sort of to the next slide and this is going to be hidden, but let's just fix that this is our goal right now and that this is a good thing to try and remember. Okay, to follow the rest of this part. Okay, so let's talk a little bit about cohomological representations in more detail now. So again, this is probably going to review from a previous talk in this lecture series, but I want to let's just fix the particular details that we're going to use here. So cohomological representations, as we said before, it means that the representation appears in the L2 cohomology of locally symmetric spaces for this group at infinity. Okay, so if you care about the classical cohomology of locally symmetric spaces, these are the representations of the real group that you're going to end up caring about. So they've been explicitly classified by Vogt and Zuckerman, and well, I guess maybe there's some extra work of Serna that this classification is it actually exhausts everything, or unitary. And the main invariant, again, is this infinitesimal character, which we'll denote by lambda. And for cohomological representations, this infinitesimal character, it's again, just like for discrete series, it's valued in finite dimensional representations of the group at infinity. So you can think of it in that way. Okay, there are finitely many for each possible infinitesimal character lambda. So that's pretty great. And well, discrete series are a special case of cohomological representations. And all the discrete series inside pi discrete lambda have infinitesimal character lambda. So everything's consistent with what we were talking about before. Okay, and sort of one important thing here is that if lambda is a finite dimensional representation with regular highest weight, then there are no cohomological representations except for discrete series. So the non-discrete series ones are exactly in kind of the sort of the exceptional case that we were discussing before, where the finite dimensional representation has irregular highest weight. So I think I do have to warn here that I'm sort of normalizing things differently than maybe the way you'll say highest weight. So what I'm saying here is that the infinitesimal character, I'm thinking of it as valued in finite dimensional representations, and I'm talking about the highest weight of that finite dimensional representation. Normally the infinitesimal character is a weight, and there's a kind of there's a row shift, right? So this is a technical note for the people that have seen this before, just to make sure that there's no confusion about normalizations. There's a row shift from the infinitesimal character as a weight, right? So just in case you were confused, right? Because normally you would think that it's the infinitesimal character minus rho needs to be regular, but I'm sort of using a kind of different normalization that I'm matching the infinitesimal character to the finite dimensional representation. I'm looking at the highest weight of that finite dimensional representation. So okay, so that's just a caveat. Okay, so that's what we're going to talk about for cohomological representations. And basically so remember what we wanted to do is our first step is we wanted to write down some kind of thing that has the cohomological pieces we're looking at, plus a bunch of extra noise that we're going to cancel out. So we have to first figure out how to write down that thing that even includes the cohomological piece that we care about. And basically what we're going to do that is we're going to take advantage of the reason why the old Arthur 89 result didn't work for these specific weights, for these specific irregular highest weights. So here's how it's going to work. So remember we had these pseudo coefficients. If we had a discrete series inside some discrete series alpacat, then well, we can construct this pseudo coefficient which will just denote phi sub pi d. And the trace against any representation at infinity of this phi sub pi d is just an indicator function whether the representation matches pi d. Now, of course, this was approximately true. This was a technicality. And the way to fix that technicality is, again, you need lambda as a finite dimensional representation, needs to have regular highest weight. So basically what happens otherwise is when it doesn't have regular highest weight, you're going to pick up the cohomological things. So these cohomological things now are what we care about. So we're actually going to focus on these pseudo coefficients. So now this technicality, this is a feature, not a bug. Okay. So the actual way we formalize this is we're going to define something called an Euler-Poincare function, which is just the sum of all the pseudo coefficients over the L packet. Maybe with some kind of normalization, you can have it there, you can not have it there. And what happens is that there's a theorem that the trace against a representation of this Euler-Poincare function is 0 unless the representation is cohomological with infinitesimal character lambda. And when it's non-zero, it's computable in terms of the Vogel-Zuckerman classification. So there's just some invariants that appear in that classification, and it equals one of those invariants. So, and even better, the symbol of half of Arthur 89 still applies. So we can explicitly compute the trace against the entire L2 space of this when we have this Euler-Poincare function at infinity, and it becomes a nice sum over automorphic representations of the trace at infinity times the trace away from infinity. So this is great. Here's our little piece with the noise. It's going to contain our cohomological terms so we care about, and it's going to contain some other terms. So what we want to do is we want to start with this, and we want to cancel other things out. So far, so good. Our heuristic framework is working out very perfectly. Okay, right. So yeah, the heuristic framework is working out very perfectly. So we're going to use pieces from other groups to isolate the summands with pi infinities exactly equal to a cohomological representation and cancel out every other cohomological thing with that infinitesimal character. Okay, so now before we get into how we do that, we have to talk a little bit about the endoscopic classification. So I tried very hard in this talk to sort of minimize the number of things I need to tell you about the endoscopic classification. So just as we're going, I'm just going to have a bunch of black box input slides that are just black boxes that come from the endoscopic classification. So, but we need to fix some notation and maybe some orientation of what exactly the endoscopic classification is trying to do first. So the goal of the endoscopic classification is you pick a group G that isn't GLN, and you want to parameterize discrete automorphic representations on G in terms of automorphic representations on GLN. So why would you want to do this? You want to do this because there's been a lot of work done specifically for automorphic representations on GLN. So there's a lot of known information there that isn't known on other groups. And you can sort of pass that information through the parameterization, and you can get a lot of powerful information about automorphic representations on the other group. So the two technical pieces of information are basically there's a Monglio-Walsh-Berger classification of discrete automorphic representations on GLN in terms of cuspidal automorphic representations, and there's also local Langlands. So this is sort of intuitively, maybe motivationally, what the endoscopic classification is trying to do. When you actually read it, it ends up being stated in terms of two key concepts. So the first key concept is something called an Arthur parameter, which is usually denoted psi. And basically, you should think of that Arthur parameter as an automorphic representation of GLN, but it's not just an automorphic representation of GLN. It has some decorations and encoding to sort of emphasize all the known information on GLN. Then, associated to these Arthur parameter, there are things called Arthur packets, which are basically subsets that partition the space of global automorphic representations on G. And because they have the structure of the local components of the representation inside these subsets, there's a lot of particular technical information you can get on the structure of those local components. So this is what Arthur's classification tells you. Okay, and what possible groups can we do? Of course, this only works for some groups. We don't have this for all groups. So by Arthur, we have this for orthogonal or symplectic groups. By Mach, we have this for quasi-split unitary groups. And by Cletham, Ingestion, and White, we have this for general unitary groups, even the non-quasi-split ones. Where general unitary groups, basically you have some quadratic extension and you do some nice enough inner form of the quasi-split unitary group corresponding to that quadratic extension. So these are the particular groups where the endoscopic classification works. So now let's talk about the actual strategy. So the actual strategy for how we're going to kill all those that extra noise. So the strategy is going to be based on another concept in the endoscopic classification called the local packets. And we're going to focus on the local packets at the infinite places. So how this works, so this is sort of getting into how the Arthur packets have a determined structure of local components. The kind of way that's stated is if you have an Arthur parameter, then in each place V, you get a local Arthur parameter psi V, and that psi V corresponds to a local Arthur packet. And basically, the local Arthur packets, you can think of them as basically coming from this kind of consistency condition, that if you have a global representation pi inside an Arthur packet, then its local component at V needs to be inside of the local component at psi V. Okay, so that's great. Now let's talk specifically about what's happening for cohomological representations at infinity. There's this really nice fact about the Arthur packets at infinity, that if you have one cohomological representation inside an Arthur packet at infinity, then the entire packet is made up of cohomological representations. So we're going to basically use a two-step process to cancel out all the noise. So what we're going to do is so first of all, there's a very important technicality here that tripped me up a lot when I was learning this, that these are not disjoint. The global packets are disjoint, but these local packets are not disjoint. So what you can do is you can pick your pi zero, the cohomological thing that you want to count automorphic representations with that component. Then you could look at each Arthur packet psi infinity zero that contains that representation pi zero. And what you can do is you can try to compute this. So you just look at the Arthur packets. So this is some disjoint division of the automorphic spectrum. And you can just look at the pieces where the psi infinity is equal to the psi infinity zero. Then you sum over the automorphic representations in there, and you just look at the trace against those specific automorphic representations that live in those pieces of the parameters. So that's our step one. And then step two, they're basically some purely endoscopic techniques that let us turn this into our goal. So if we can cancel things out to get this, then if we can cancel out noise to just get this, we just have to cancel to this. We don't have to cancel all the way. We can just cancel partially to here. Then there's some purely endoscopic techniques that let us cancel all the way. So we're going to skip this because that sort of brings us a little too far afield. We're just going to focus on this step one. Okay, So let's input our black box for step one. So they're going to be two black box slides. So we're going to pick and allow G. So the automorphic spectrum is partitioned into Arthur packets, and we can write that as some approximate inequality of trace heuristically. So this is again heuristically. So the trace against the entire discrete L2 is going to be the sum over the traces against each of these packets. So for every Arthur parameter psi, we get a smaller group H sub psi and a parameter psi prime on H, so that we can think about this transfer operator, and there's some conjectural transfer that the trace against the this trace against the packet on G corresponding to psi of F is going to be the trace against the packet on H of psi prime of the transfer. So H is general, for those who know, H is going to be more general than an endoscopic group. And the existence of this FH is conjectural. It's sort of suggested by the form of the endoscopic classification. So in terms of our heuristic strategy, we can think about the trace against the part coming from H as basically the trace against all the packets that correspond to group H. Yeah. Okay, sorry. So let me move on to the next black box input. So the key useful idea here is that H sub psi, this group that's determined by the parameter psi, is actually determined not by psi, but you can sort of factor it through a useful invariant of psi called the shape of the shape. And we'll denote the shape by this delta sub psi. So there's a lemma that if you have a parameter for G, and if the packet at infinity contains a cohomological wrap, then the component at infinity depends only on the shape. So this is a useful invariant. This is why it's a useful invariant for our cases. So basically, we're going to do something slightly different than the heuristic that I said. Instead of breaking things up by this H sub psi, we're going to break things up by the shape delta sub psi. So we're going to refine it a little bit further than just looking at the pieces for H sub psi. We're going to look at pieces for delta sub psi. And because the delta determines the psi at infinity, if we know all the pieces for delta sub psi, then we know all the pieces for the psi at infinity, for psi sub infinity. And that was our original step one goal. So, okay, so we're going to do this sort of slightly more refined thing than the piece for H. We're going to do the piece for delta instead, which we define in a very similar way. And we still have some kind of conjectural transfer identity. If you have the transfer to H, there's some formal manipulation you can do that the piece for delta, it doesn't become the full piece for H, but it becomes the piece for the sort of trivial shape. So there's a trivial shape that's sort of specially set aside, a shape such that the group associated to the shape is literally the original group you started with. And the piece for any shape becomes a piece for the trivial shape on the group associated with that shape. So we can still use the same framework. We just have to refine it a little bit to these shapes, but the refinement, it sort of formally all works. If you can do the original framework, then you can do this framework. So, okay. So now basically we're good enough if we've reduced everything to being able to compute this trace against a spectrum for a given shape. And how we can do this, we basically inductively alternate two identities. The first identity is kind of a sort of triviality that if you want to isolate the piece for the trivial shape, you take the entire piece and you subtract off everything else. And the second is basically that transfer notion that we were talking about before. So basically what you do, you want to understand a given shape on one group. So you write that given shape on one group as the trivial shape on another group. You write the trivial shape on another group as the entire thing minus a bunch of shapes on even smaller groups. Then those bunch of shapes on even smaller groups between the trivial shape on even smaller groups. And you just alternate these two in some induction, and you eventually work your way down to a case that's maybe just like an abelian thing that you can compute. So this is the induction. And then all you need to do is you just have to take the sum over all shapes such that the component at infinity determined by the shape is the parameter at infinity that you want. And that solves step one. So this is sort of maybe a sort of, I don't know, a sort of example of how you can actually do these things. Okay, So I'll just take a minute for the last slide, just maybe talking about when this is actually realized. So in joint work with Matilde Gerbelli-Gauthier, we sort of applied this to homological pi knot and unitary groups. So basically, we were counting the dimension of modular forms of a fixed split level within the automorphic representations with a pi infinity that equals a fixed comodular representation, and we're taking this level going to infinity. So basically, the issues with transfers restricted the generality of the result. So for an arbitrary comodular pi knot, we were only able to prove upper bounds. And this had some analytic applications to something called the Sarnak-Chouet density conjecture. Um, and then for some very specific unitary groups and certain pi zero, we were able to get exact asymptotics. And these are basically exactly the special cases where the transfers needed were already known. So again, we just piece together already known cases of the transfer until you can actually get a result. And there's some number theory applications there. There's sort of a Sato-Tate equidistribution on average that's sort of very analogous to the Shin-Template result. So we talked about a lot of heuristics, and we talked about like, okay, there's basically this bugbear of this conjectural transfer hanging over everything, and but it's you can still get results just by doing special things in the special cases that you care about. You can still get results, and hopefully this paper hopefully demonstrates that. Okay, so I think that's everything I wanted to talk about. Are there any questions? And yeah, thanks to everyone for listening.
Yeah, thank you. Yeah, so are there any questions from the audience? I have some few questions I'll ask. So, like, finally, in the case where you are having this example result,
Mhm.
so here still, like, do you need to assume some sort of like local Langlands kind of statement, like, or you don't?
I think the specific result we had, we didn't have to assume any kind of local. No, so we were using the local Langlands that came from the endoscopic classification.
Yeah, that's exactly. So, like some classifications, like the L packet or something, are you going to use it, or like it's
Yeah.
independent?
So this is dependent on, okay, so one caveat that I didn't mention is that all these endoscopic classifications, there's some references in them that are not publicly available yet. And
Okay.
I'm not sure how much the authors have actually written them out yet.
Hmm.
But I think, I don't know, Arthur expects them to be true, and he says
Yeah,
that like,
it's just people
it's been
believe
like that
Arthur
for
and
years. Uh,
yeah,
yeah,
okay,
so
okay,
yeah, so in every paper you have a little caveat section at the beginning that say this
yes,
is dependent on the sort of the this is dependent on the pieces that aren't publicly available yet. Yeah.
yeah, okay, okay,
Yeah. So yeah, everything once the endoscopic classification comes in, everything's dependent on that. So
yes, yeah, okay, I see.
yeah, yeah.
And
And then
the second question would be like again when you are saying that it's reduced to the fundamental lemma, so this is known by whom? Like who proved this for the
oh,
like
oh, this
this
is
was
just
the is this
well,
like
okay, so
from this no like this Chow
yeah.
Nobel
It's just Niels
Nobel
van Belhammer,
yeah
right? But
okay
it's a little bit more than that. There's a little bit of Arthur's classification on top of the fundamental lemma. So with the formalism of the Arthur's classification, it gets reduced to the fundamental lemma. So
okay
which basically is you can think of it
yeah
as a really big black box. We're really happy that gave this to us. So, so
okay
it's
okay yeah
yeah.
because I mean like there's this recent results by Thorne and Newton about the symmetric powers and like
Oh,
this like what they prove this arbitrary symmetric powers are like cuspidal kind of like automorphic
right.
yeah
Right.
so those are
They use
so
Alva representation techniques though, right?
yes exactly
Yeah.
yeah and they do get also some kind of supported applications
Yeah.
finally
So they can once you get the symmetric powers, you can do like better things, right? Because
yeah
this is something on average, right? So what you have to do is you have
right
to you have to look at all the components for like some family of automorphic representations as growing to infinity. And if you get all the symmetric power functorialities, then you can look at a single representation and get a Sato-Tate law for just that one thing, which is pretty awesome.
Just that.
Yeah.
Okay.
Yeah.
Yeah. Sorry. Any other
We
questions?
had a talk about that in the seminar, right? Like a little bit earlier, maybe Northeast talk explained exactly how that worked. Yeah.
Okay. So any other questions?
No, perhaps.
Okay. So if not, let's thank Rahul again. So, thanks.
Thanks,
Yeah,
Rahul,
thank you.
for some wonderful